CoCoA-Mix, Confusion and Confidence-Aware Mixture Model for Context Optimization. Pre-trained vision language models have demonstrated their strong open-set and zero-shot capabilities. However, their reliance on generic embeddings often limits their effectiveness in real-world deployment. The figure below highlights how prompt tuning can help adapt pre-trained VLMs effectively to real-world environments without the need for full fine-tuning. Our approach focuses on textual prompts tuning of CLIP, one of the most widely used vision language models. To perform image classification, we can input prompts like a photo of a class into the text encoder, and compute the similarity between the resulting text and image features. The model predicts the class with the highest similarity score, and the probability for each class is obtained by applying softmax over the cosine similarities. The expected error of a predictive distribution in an arbitrary target domain is defined using the KL divergence as follows. We introduce a mixture model to derive an upper bound for the error, providing a framework for analyzing specialization and generalization. And the expected error can be upper bounded as follows. Now, if we split the target domain into multiple disjoint subdomains, the error of the mixture model can be expressed accordingly. By combining this with Theorem 3.2, we get an upper bound consisting of a specialization term and a generalization term. We assume that labeled data is provided for domains of large T_1 to large T_k, whereas no supervision is available for the domain of large T_0. Due to the absence of labeled data in the domain of large T_0, we utilize a generalized handcrafted prompt such as a photo of a class. Building on this, our proposed method, CoCoA-Mix, aims to reduce the upper bound of target domain error in terms of specialization and generalization. To do this, CoA-Loss improves specialization by focusing on confusing classes. And CoA-Weights enhances generalization by controlling the mixing weights based on confidence for the given domain. In traditional prompt tuning, standard cross-entropy loss is widely used. While effective for misclassified cases, it relies only on individual probabilities and does not consider interclass relationships, limiting its ability to handle class confusion. In prompt tuning, confusing samples are very important because they significantly impact the decision boundary with frozen encoders. To overcome this limitation, we propose confusion-aware loss, defined as follows. The overall loss for optimizing the prompt T is a weighted sum of cross-entropy loss and CoA loss, with a hyperparameter controlling the balance. As implied the equation, CoA loss increases the gradients for y when the probability of y approaches to 0.5 and for class C when the probability of C nears that of y. These scenarios represent confusing cases where the correct class probability is uncertain or where the incorrect class probability is similar to the correct class, making them difficult to distinguish. CoA loss thus induces larger gradient updates for these confusing cases. Now, let me explain CoA weights. The equation also suggests that optimizing the mixing weights, pi, can minimize the upper bound of the expected error of the mixture model. To achieve this, we first assume that the specialized prediction satisfies the following relationships. Based on the assumption, we can now optimize CoA weight for in-class domains. The weight is optimized by minimizing the cross-entropy loss of the mixture model over the training domain. With this optimization, the in-class weight is increased when the specialized prediction outperforms the generalized prediction for the in-class domain, and decreased otherwise. The weight for out-class domains is optimized using entropy loss, which compares the entropy of specialized and generalized prompts as follows. The entropy loss ensures that the entropy of the specialized prediction exceeds that of generalized prediction by a margin of d. The table shows that CoA loss enhances the base performance effectively but shows limited generalization as it only focuses on specialization. By incorporating CoA weights, our CoCoA-Mix achieves the highest average performance on both base and new classes without trade-offs. This also shows that our method effectively transfers learned knowledge to new domains. This experiment evaluates CoCoA-Mix in the few-shot class incremental learning setting. This shows that CoCoA-Mix is effective in both adapting to new tasks and retaining past knowledge. We conduct ablation studies to evaluate the effectiveness of CoA loss. As shown in the bar chart, CoA loss consistently improves specialization performance compared with other loss functions like CE or GCE. It also significantly boosts performance on confusing samples, as illustrated in the plots and right-side improvement chart. These results confirm that CoA loss is highly effective at both specialization and handling confusing samples. This slide shows how CoA weights contribute to generalization. As seen in the table, optimizing both in-class and out-class weights gives the best harmonic mean, improving performance on both base and new classes. We also evaluate CoA weights' sensitivity to the outclass set generation strategy. The results show minimal variation across different methods, indicating that CoA weights are robust to how the outclass set is constructed. Thank you for watching. For more details and in-depth results, please check out our paper.